And I'm going to share screen. Okay, so what today we will do is I'm going to give some idea about another type of neural network for the deep learning as RNN. Okay. So previously, we learned artificial neural network, ANN. We also learned the CNN, convolutional neural network. Okay, so this is another one, RNN. So let's take a look. Okay. Okay, so the first is about the concept about the RNN. So R represent recurrent neural network. Okay, and if you recall ANN, so artificial neural network, so generally speaking, the neural network previously, what we learned is feed forward neural network, okay? And so what RNN is, so it says it works on the principle of saving the output of a particular layer, okay? And then it says it's going to feed this back to the input for prediction of the output layer. So here there is a little bit different from what we learned is feed forward. Okay, so here the output of a particular layer will feed back to the input. And later on, we will also see that why we do this is because of the data has sequence. So there is order, like a timeline, something. Okay. So here is an example. Okay, the idea. So here the t represent certain time. So time t minus 1. So t is the current time, or we call current state. And then t minus 1 is one time step ahead, so before. Okay, so this is one time step before the input. So x is input and y is the output. Okay, so what over here is going to do is, so at time t minus 1, is it you train the neural network, you will get some output y minus 1. So at that time, okay, and here is regarding the hidden layer. Okay, so the hidden layer will generate some output. And then if you take a look here for this current state, so its input is not just from X. It's also from the input from the previous time stamp generated output. So there are two parts of input for this training, for these neurons to do the training. Okay, so one is the current input, the other is previous time stamp. Time stamps is output. It will be feed. So that's why over here it says feed this back to the input, so that we do the training and generate this time stamps is output. That's why we have this word recurrent. Okay, so it's we have the prefix re, etc. So you feed this back. And then the same thing for the next time step, you have the current one, and then you also have the one from the previous time step. So the input part has two input part. One is from the current input and one from the previous time step. Okay. So this is what is a current recurrent neural network. Okay. So the very general we will see in of the literatures and the materials, whenever we draw a recurrent neural network, it's this simplified flow. Okay, so you have input, is it? So this is the neuron part, the hidden layer parts. So it's going to be trained, is it? But it's feedback as the input. And then both of them together will be trained again to generate the output. Okay, so the recurrent neuron, so this is a recurrent neuron, it stores also the state of previous, okay, timestamps as input, and then to combine with the current input, okay, to generate the output. So anyway, so here, just remember whenever we see t is a time step t, okay, at a certain time step t. And the H here we represent a hidden layer output. Okay, so for the neural network, then the hidden layers output, we can express it as the current timestamps input. This W is the weight. So this weight is regarding your input to the hidden layers neuron, okay? And here we have HT minus 1. So this is the previous layers output, okay? So this is not previous layer, I'm sorry. So it's previous time step T minus 1 output. Okay, and this output, then you times the weight. So this weight is regarding the output from the previous and to the neuron. Okay, so this is feedback, the weight. So these two weights are different. And then apply to some function. Okay, later on we will see we use a lot of sigmoid or the tangent. Okay. So anyway, so F is some activation function. Okay. And so this is a general picture regarding recurrent neural network. And here is that we can unfold it to better understand it. That then it's go back to the previous slide. That so here is the current input, and here you have the previous timestamps output, but you're going to feed to this neuron and train it, and then you are going to generate the output for the hidden layer. Then you apply some operation, and over here for the output y, and for the current time step. Okay, so this WHY is the weight between the hidden layer and the output, and then the same thing for the next time step. So this is a general idea about what is a recurrent neural network. And next, let's see, why do we need a recurrent neural network? The reason behind it is that, so for the previous neural network, it's a feed forward. Is it? So for feed forward cannot handle well for sequential data. So sequential data, that means your data set depends on time. Okay, one of the most mentioned is like a stock market. Is it? And sometimes we also have like weather forecast. Is it? So it depends on time for sequential data. If we just use feed forward, it cannot handle that kind of situation. Okay, and also for feed forward, it only consider current input. It ignores the previous timestamps input, is it? And also it cannot memorize previous input. Because a lot of time when we do prediction, the prediction rely on sequence, is it? And the sequence of here, what we can also mean is regarding the time, is it? Regarding then, for sure, you need to be able to remember the sequence pattern, is it the time pattern, so that you can make the correct prediction. Otherwise, if we just use feed forward, that cannot achieve the goal. Okay, so here is the reason why we need to do that. Okay, so here it also gives us a comparison between a typical ANN. Okay, typical ANN, we know it's we have the input, etc., and then it's the weight between the input and the hidden layer, etc. Generally speaking, we then also conduct activation, etc., and we can choose, if you recall, this is the rectifier linear unit. Okay, we use that a lot for neural network. Okay, and then you are going to generate output from the hidden layer to the prediction, is it? And for neural network, a lot of time we use softmax. Okay, so that's just go all the way from input to hidden layer, then from hidden layer to output. So that's why we say it's feed forward. But you may ask, we also previously, when we discuss gradient descent for neural network, we also discuss the concept, we call it back propagation. Is it back propagation? So for the back propagation, it's regarding the gradient descent part, okay? But overall, for neural network, it is feed forward. Then a typical RNN, recurrent neural network, what it looks like. So a lot of time, recurrent neural network also used for like natural language processing. So anyway, something related with language. Whenever we mention language, so like in this case, all weights and bias are the same, is it? So they are in sequence, and it depends on the previous word, is it? So what over here, we use this as an example, is it? So each time your input is a single word, is it word one here, is it? And then you move to the next, you have the second word input, therefore and then you have the third word input for the activation. And then you can predict what the fourth word is based on the previous three words. Is it? That's how we kind of train the language using neural network. Okay. So here it involves the recurrent, is it? Because for the second word, it also depends on the input of the first word, what that word is. And for the third word, kind of look back to history. History input, is it? It also has some impact, is it? Yeah. So this is also why we need a recurrent neural network. And what the next discussion is about applications of recurrent neural network, okay, RNN. One application is we call image caption. Okay, image caption is you have an image and then, so here is a caption. Is it a sentence describe what the image is? So in this case, it's a dog catching a ball in mid-air, something, is it? So this kind of, later on, we will also see various different types of recurrent neural network. So in this case, the input is one, is it? And here is the output. So input is one image, and output is what? It's a number of words. Is it? So number of words is then what? It's many. So then the relationship is one to many. Okay, so this is one to many type of recurrent neural network. And then some other application also involve like time series prediction. Okay, time series prediction. So anything involve time series, like we predict stock price, is it? And this we can solve using RNN. Okay, and also like natural language processing. Okay, as a text mining and the sentiment analysis, is it can be carried out using RNN for natural language processing. Okay, and sentiment analysis basically is you have sentences, so a number of words. So this is many, is it? And then the sentiment is just a single word or a sign, is it like happy? Is it something like this? Is it? So there's just a single one. So this is one. So then this is many to one relationship. Is it? But there is also something else. Okay, like translation. So language translation, is it? So like this is English. And maybe you translate to Spanish. So it's also a sentence. So a number of words to a number of words, is it? So this is many to many relationship. Okay. And for this, like the time series, then it's many to one because you just predict one. Okay. So this is the applications of recurrent neural network. Okay, we can say, okay, like what we just said, machine translation, is it? You can also use recurrent neural network. Okay, and type of neural network and one-to-one. So one-to-one kind of neural recurrent RNN, we also call it vanilla neural network. Okay, it's a use for general machine learning problem. So you have single input and a single output. Okay, so this is 1-to-1. We have one-to-many. We just saw it like image caption. Is it because the outputs is multiple? Okay, we have many-to-one. Is it so many-to-one like a sentiment analysis is many-to-one? Is it? So you have sequence of inputs, but you just have single output. Okay, so the input is still sequence of input. Okay, and what is many-to-many? Many-to-many is sequence of inputs and generate a sequence of outputs, like translation. Is it like language translation? Is many-to-many, okay? Because you have number of words to a number of words, okay? So this is a type of, and also keep this special word, vanilla neural network. That means one-to-one RNN, okay? Okay, and the standard RNN, okay? So the standard RNN, it's kind of looks like this, okay? So the current input, so basically for current state, so it depends on current input and previous time step hidden layers output. So it just depends on the previous times, just one time step. Okay, just in that case, so this we call it standard RNN. Okay, so it just depends on the previous time step. Then it can cause a problem. We call it vanishing gradient problem. Okay, vanish gradient problem. So vanish gradient problem, here it says recurrent neural network will let us to model time dependent, is it? And sequential, be careful, okay? It must be in sequential time dependent problem, is it? And as previously, we already see it's a stock market machine translate text generation, is it? But if we just use that, then it's hard to train, okay, for the RNN because of the gradient problem. Okay, that problem is called vanishing gradient problem. So vanishing gradient problem caused what that is, it's the gradient carries information that previously we learned. That gradient is used to update the weight. That's for the gradient, okay? It's based on the loss function or cost function. Or loss function, is it? You take a derivative. And regarding weight, specific weight, take basically it's a partial derivative as a regarding weight. Okay, and if we use the back propagation, then we can avoid huge number of matrix multiplication because that's not going to be efficient, okay, for machine to do processing. So we can do the back propagation, okay. But if we use back propagation and do the gradient, then it says gradient can become extremely small for RNN. When gradient becomes extremely small, then the parameter updates is insignificant. So basically you will not have any updates for your weight. Is it? If you cannot have significant updates for your weight, then the learning of the long data sequence is going to be difficult. is it? So this problem, we call it vanishing gradient problem. Okay, the other problem is called exploding gradient problem. Okay, exploding gradient problem is that if the slope grow exponentially, is it, instead of decaying, okay, then it's called exploding gradient. And exploding gradient can happen when large error gradients accumulate. So that's also a problem, okay? So those are the issues. Okay, for the solution, gradient problem solutions, one is vanishing and then one is exploding. So for exploding, then what it can take is it's said identify initialization and then you truncate it back propagation, okay? Then we also take a gradient clipping, okay? And for vanishing gradient problem, we can take weight initialization as part of, and choosing the right activation function. So previously we also discussed, is that there are different activation function. In neural network, we use that ReLU a lot, is that in ANN, and it's because it has some benefits, is that okay? And for vanishing gradient issue, then one of the solution is we use long short-term memory network. So basically in RNN, we see this a lot, LSTM. So LSTM is called long short-term memory networks, okay? It has a lot of short-term memory. Now, so what that is, so that's what next we are going to discuss, okay? It's more complicated than the vanilla one. The vanilla one is quite simple, because it's just depends on the previous time step, okay? So the standard, not just vanilla. So the standard RNN, it just use previous time steps output. Okay, so all of the other previous one, they are going to ignore, okay? But let's see what LSTM is. And why we need LSTM, okay? How can it help the problem? So here is an example. It says for the vanilla, it said RNN grade when it comes to short-term dependency. Okay, short-term dependency. Shorter is because it only count on the previous time step. Is it? So here is an example. It said the sky is blue. Is it? So the prediction of the blue is in the sentence sequence. It just depends on the previous ones. Okay. And it says RNN then will fail to predict long-term dependency. Okay, so for short term, so this works okay for short term. But then next, let's see, okay, because here, blue and the sky, this is the short term, so it works. And the long term, so let's see, we have this sentence. It says, I have worked in Spain for 20 years. It says, now I'm in US and I can speak fluently Spanish. So this Spanish prediction of Spanish, then it's across 2 sentence sequence. So it's not in a single sentence, it's across multiple sentences. And when we do natural language processing, whenever we have an article, we also have paragraphs. Is it? So paragraph is a multiple sentence. Is it? So maybe the first sentence and the last sentence, they have strong relationship. Is it? So how can we also keep memory of the first sentence? Is it when we predict the last sentence? Because over here, the Spanish and Spain is across two different ones. Okay, two different ones. Okay, and so this is the shortcomes. The shortcomes. And here says in order to build a story and remember it, is it? So we need our models to understand and remember the context behind the sequences. So we need to also have long-term memory. Okay, long-term. So we have this long short-term memory networks. Okay, so let's see what that is. So what improvement is that basically this long short-term memory is an improvement over RNN. Okay, over RNN. So LSTM, it can make small modification to the information, okay? And we will see by using multiplication and addition. And for LSTM, we will also see that information flows through, we will call it a cell state, okay? And the network can selectively remember or forget things. So when you have a paragraph, you may have multiple sentences. So this is the first sentence. This is the second one, third one. Maybe this is the 10th sentence. Is it? So you may select to remember, okay, I will remember the first sentence. I will remember the second one, not important, so I can forget. So that's what it means. You can selectively remember or forget. Okay. Then the information at a particular cell state. Okay. So it will have 3 different dependencies. So what are the 3 different dependencies? So here we describe them. So there is a previous cell state. Okay, so this previous cell state is as information that was present in the memory after the previous time step. So it's not just that previous time step. Okay, it also include the history data. Okay, so here is a difference. So not just T-1 time step information. Okay, so it may also include like maybe T-2, T-3 something. Okay, so multiple time steps. So history is going to remember. And the previous hidden state. Okay, and the input at the current time step. So that's going to be the new information fed into the moment. Okay, so that's the information. Okay, Then let's see the architecture of the LSTM. Okay, so there are 3 parts. Okay, be careful about LSTM. 3 parts. The first part is I choose whether information coming from the previous time step is going to be remembered or not. Okay, so this is the first part. So we will make a decision if we want to forget irrelevant information. Okay, and the second part is about the new information. So the current one, the current information. Okay, and the third part is to say it will pass the updated information from the current time step to the next time step. Okay, so it will pass. So that's the third part. So a cell includes 3 parts. Okay, later on we will also say it's quite comprehensive. And because of the 3 parts in LSTM, we also call them 3 gates. 3 gates. So the first gate, we call it forget gate. So forget gate will determine if the information will be kept or not. Okay, and the second part is called input gate. And then the third part is called output gate. Okay, so that's regarding the term for the cell. Okay, and then let's see. Here it says, because anyway, LSTM is also recurrent neural network, etc. So it has a hidden state. Regarding the previous time step, we call it T-1, etc. So it represents the hidden state of the previous time step. Be careful, okay? And HT is the hidden state of the current time step. Okay, and be careful here is it's not in the standard one. We only have this H, hidden state. Okay, but for LSTM, we also have, we call it a cell state. So here in this diagram, we see this is a hidden state, is it? And this is a current hidden state, H. Okay, so basically the hidden, then we call it short-term memory. So the previous time step, okay, this is short-term memory. But in LSTM, we also have cell state. It's represented by CT-1 and CT. Okay, so then what that is it? So basically, this is called long-term memory. CT-1 and CT, they are called long-term memory. So H is for short-term memory. C is for long-term memory. Okay, that's how we come with long, short-term memory. Okay, so short-term is just regarding previous timestamps, hidden state information. And C is long-term, okay? So including all of the previous timestamps, information, okay? And then we ask, how do we do that? Is it? So that's next, let's see. Okay, so it's a kind of comprehensive, okay? So here, X, so all those represents input. Is it inputs from different time steps. Be careful, it's time steps. Okay, so here it's regarding hidden state output. Be careful, this is not Y, okay, not Y. Y is called a target value. This is just a hidden layers output, okay. And over here, this sigma represents sigmoid operation. And tangent, we also learned, is that it's also a kind of activation function. Is it? So what this diagram means is, so let's see. So here is, you're going to apply current input and the previous, so this is H, is it? So the lower arrow represents short term. Short term basically just previous layers. So anyway, so it's H part, is it? So the H part and the input part, so X maybe times some weight, is it? And plus the H part, is it? Also times some weight. Then you apply the sigmoid operation together, is it? So that's what this part means. Okay, then they are going to generate some output, is it? And here, this one is what? This is from long term. Long term. Okay, from the long term, and then these two going to multiply together and then feed to the next step. Okay, so that's general idea. So next, let's take a look step by step. Okay, so we already understand the cell state, hidden state. Okay, and this diagram is kind of similar as the previous one, but has more information. As we already explained, is it the lower arrow one represent short-term memory, and this upper one represent the long-term memory. Is it? So this is a cell state. This is a hidden state. So this is a hidden state. Okay, and this sigma represents sigmoid. It's some activation function. Okay, so it's going to keep flowing like this. Okay, so quite comprehensive. So let's take a look one by one to understand it better. So if we go back to the previous one, is it? So this means some operation, okay, for the current time step. Okay, so what that means? So over here, so how LSTM works, is it? So the step one says it's going to decide how much past data should remember. Okay, then in this one, it's going to determine which information should be forgotten. Okay, should be omitted from the cell in that particular time step. Okay, it's a sigmoid function determines this. Okay, so here is a sigmoid activation, is it? So here you have the current input. This is previous layers, not previous, the previous state. Previous states is output, is it? And this is the weight. Okay, and this is a bias term. Okay, and then you apply the sigmoid. Okay, so this will give you some output. The sigmoid generates some output between 0 to 1. Okay, generate some information between 0 to 1. Okay, if it's generated some information between 0 to 1, if we go back here, then just think about if it is 0, the sigmoid, and then here you times the previous. So then that means you're going to forget. So completely omit it. Is it? And if it is 1, then you times this, then it's going to be remember. Is it? So that's why we see it make use of the the long-term memory. Is it long-term memory? But it's determined by this activation function. Is it based on the input and the previous timestamps hidden there is output. Okay, and the long term, it will have impact or will not. Okay. So that's regarding that. And then what next one is, then it's also going to decide how much this unit going to add to the current one. Is it? So it said there are two parts. Okay, one is the sigmoid, the other is the tangent part. So the sigmoid as usual is decide which part you can let it go, is it? And what a tangent basically is just try to normalize data. All we can see, we are going to skew the data because tangent, the result is between 0 or -1 to 1. Okay, so it's still based on the hidden and the current, is it? So this, if we go back here, is it? So here, this sigmoid, it will take x, t, it will also take h, t minus 1. So the short-term memory and the input. So this is a sigmoid, is it? So it will determine if it's going to be remembered or not. And this tangent, it's the same thing. It will take xt and take ht minus 1. And it will vectorize the data. Is it? And both together, you multiply that. Is it? Because if it's 0, then that means totally forget. If it is 1, then this part you will consider that. And then what over here it means is this part result also calculated, is it? And then it's going to do addition, add, is it? So if the multiplication result is not 0, so that means long-term memory. So basically history will be taken into consideration. As it will be taken into consideration. Okay, and then move on to the next step. Okay, and we kind of run out of time.